So, okay. Okay, yeah. Before we get started, I kind of spoke to Kaushik. I think I'll kind of record this and put it up on YouTube publicly later once Professor Anand's kind of gone through, and hopefully I'll pass today. So if you have any issues with being recorded, please let me know. I can kind of mute out your questions or anything with respect to the recording and online. Or you can just, if you're not comfortable sharing that here, just send me an email separately or come talk to me separately. So I'll get started. Oh, okay, sorry. Yeah, today I'll be talking about my work towards trustworthy AI, understanding memorization, privacy, and security in deep learning. I'll give you a quick overview of the slide presentation. We'll talk a little bit about what trust is and what the pillars of trustworthy AI are. I'll give you a little bit of background on things that are needed to kind of understand some of the research that I'll be presenting. I'll give you a quick one-slide recap of the research that was presented in my prelim. I'll talk about the privacy pillar, which includes two components, which is a theory work that links memorization, input curvature, and privacy, and a new membership inference attack paper. And finally, I'll talk about the memorization pillar, which talks about two new proxies for memorization. One which is fast, one is even faster. To answer what trustworthy AI is and how we can kind of move the frontier on trustworthy AI, we need to really understand what trust is. Trust is defined as the willingness of one party to be vulnerable to the actions of another, based on the expectation that the other will act in a way that's beneficial or at least not harmful. So in this case, let's say we want to be able to trust AI. We need to be able to trust that AI will act in a way that is not beneficial or at least not harmful to us, even when we don't have direct control over the AI. Back in 1998, Flores et al. Kind of defined levels of trust. This was not with respect to AI, but in general. It goes from blind trust all the way to articulate trust. And I want to kind of quickly go over how this maps to the pillars of trustworthy AI, and how we'll talk about how the pillars of trustworthy AI map to my research. Blind trust is the simplest form of trust. It might be just like a baby trusting everything will be all right in the world. You have complete faith based on no notion of previous history or anything. Then we have basic trust. Basic trust is what we would expect most modern AI systems to be, which is maybe robustness to some sort of adversarial inputs or out of distribution examples, where we can trust that the network is not going to make huge errors. Then there is authentic trust. Authentic trust is more of like a PhD student using AI, right? So you know there are big problems with AI in terms of trust. So you kind of balance out trust with, oh, this might not be correct. Maybe I need to double check the output. That is authentic trust. And then we have articulate trust, which is the most formal notion. It might include government regulations saying, oh, we need to have this kind of performance guarantees or fairness guarantees. And what I've done here is kind of mapped the colors of the trust to the pillars of trustworthy AI. Basic trust really maps to robustness. So like I just said, basic trust means we kind of think about, oh, it's going to work. We don't think about it more. When we think about authentic trust, we understand, oh, there is some probable reasons why this AI might fail. So we kind of have this weighed trust versus checking its work. And finally, we have articulate trust, which is the most formal notion. And we really need that for like fairness in your data set. Make sure all populations and subpopulations are represented or fairly represented. And then accountability in terms of AI that make decisions. Right, so this is how like the pillars of trustworthy AI draw from trust, and I'll talk about my work, which maps to the pillars of trustworthy AI. My work really focuses on three aspects: security, privacy, and memorization. while these look like three distinct areas, generally moving the frontier on one also moves the frontier on the other one. So for example, my work improves ability to test privacy on some of these models. But what we also show is improving privacy also reduces memorization. So moving the frontier on one generally moves the frontier on the other. Now we'll quickly switch gears and talk about the background, a few things that would be really useful to kind of follow the slides and research that I'll be presenting. Firstly, I'll talk about long tail data. This is a very interesting theory that kind of came out of Feldman and subsequent work, Feldman Zhang and a few other people. This is the image on the left is counting how many patterns of buses exist in the ImageNet dataset. What do I mean by a pattern? So the bus that is front view is, let's say, pattern 1. The bus that is back view partially obscured is, let's say, pattern 50. And there's a full spectrum of these that exist, right? Maybe the bus is side view, maybe somewhere here, and so on. And if you count the number of examples each of these patterns have, it follows this long tail. What is this long tail? It means lots of examples of this prototypical bus exist, but not so much of this non-typical bus. Similarly, this is the same thing for people in the ImageNet dataset. So this is like a front view of a person, side view of a person, and like the top view of a person looking into the screen typing on a computer. Right? Not only within like a subpopulation or a class, you can also observe this across different classes. For example, the number of windows in the Sun dataset versus, let's say, coffin or ziggurat, which are like much less represented. So this just plots this in log scale and shows it's linear in log scale. Like we said, most real world data sets are informally known to be long tail, and the long tail is atypical, and generally we need to memorize on the tail to be able to get generalization performance when we see these subpopulations. And there is the link that was kind of established by Feldman kind of shows that to get performance, generalization generally happens here. In between, you have this spectrum between generalization and memorization. Next, we'll talk about differential privacy. This is the formal notion of privacy, and I'll quickly go over something known as pure differential privacy, but I'll go over it as if we were to discover it ourselves from first principles, right? So what is the problem that differential privacy started off with is, can we do privacy preserving data analysis? So given a data set, imagine all the people in this room are part of a medical data set, and we need to analyze some statistics. So the data set could include, oh, person A smokes, person B smokes, person A has cancer, person B doesn't have cancer, and we need to, let's say, query this data set to identify correlations. So how do we do that without revealing, let's say, Deepak smokes, right? Or something of that sort. Option 1, we just remove the names of the people, right? We de-identify the data set. But there is this popular example of Netflix price data set where they were able to re-identify the people on the data set even though it was de-identified. So generally, de-identified data sets are not really anonymous or private to speak with. The other option is we could only release the statistics, right? So if we are only interested in the correlation, we could release the correlation. But there is this limitation. Maybe I am interested in correlation, somebody else is interested in some other statistics. And if you release enough statistics, you can reconstruct the data set. So that is a no-go. So what do we do? We'll kind of think about an example where I am in this data set. Maybe smoking is not the best example. Maybe we'll say Deepak has, I don't know, breathing issues, right? So let's say this data set is consists of people having like breathing issues versus not, and maybe some factors that affect breathing issues. And we want to be able to say things like, does this environment factor affect breathing problems? We can say, what happens when Deepak wasn't in the data set, and what do we want to learn about Deepak? Specifically, if we are doing privacy preserving stuff, you might say, hey, we don't want to learn anything about Deepak. We want to learn only something about the data set, nothing about Deepak. But that really means you're learning nothing. And so there is no point in doing data analysis. The reason being, if I were to be replaced by somebody else, you could say, I don't want to learn anything about that person, and you could do this for every data entry and you will not learn nothing. So the other option is, we can think about what happens if I were to be removed from the data set and we run the analysis, right? If we were to learn the same thing, if I was included in the data set versus if I was not included in the data set, then we are learning something about the population rather than me specifically. And that is where this notion of privacy preserving analysis comes from. Let's say we want to know how many left feet this data set has. Initially, I think everybody has 2 left feet, right? And I run this analysis and I get, oh, on average, people have 1 left feet. Now, if you were to remove me from the data set, I would still come to the same conclusion that people on average have 1 left feet. So what I have learned is not something specific to me, but the data set as a general. But this is a choice of privacy that we are making, that the way we define privacy in this case is a choice that we're making. We could have defined it several different ways, but this is how differential privacy is defined. Formally, we can just say the analysis of any outcome should be independent of if a data point was included or excluded from the data set. For a pure DP consists of, like, the way we define it is consider 2 adjacent data sets, one with 1 entry missing, and then we apply an algorithm A, and any event that follows by the application of A must have this ratio. So for example, if a statistical result had a probability 0.5, then the ratio of when that data point was excluded must be bound by e power epsilon. Let's take a simple example. Let's take this ratio and let that be 1. It means that whether let's say Dave was included in X or Y, right? What we would see is on average any event would be equally likely, which means e power epsilon is 1, means epsilon is 0. So that is the best case for privacy. So generally smaller epsilon is better privacy. We'll quickly jump over to memorization, and memorization is very similarly defined. Instead of ratios, you are looking at differences, and you're looking at differences in performance when a sample was included versus when a sample was excluded. Finally, we'll talk about some of our work that's done in NRL, which is the notion of input curvature. And this will come up again in a few of the works. So the idea with input curvature is to capture information about the data, but we do that through the model. So we train a model, we identify some properties of the model and back propagate it to the input, so we can learn information about the data using that. And the way we do that is we perturb the input a little bit and we see how the output changes, and we use that to make to gain some insights into the data. Let's visualize this more so that we get a more intuitive understanding. So here I have the input space. So this is, let's say, one point in the input space, which is an orange or a white cat, and then we have Garfield, which is an orange cat. Now this white cat is in an area of low curvature. So what does this low curvature mean? It means that the loss landscape is pretty flat and has a large radii if we were to fit a tangent here. Whereas if we were to look at this example, a cat, it is in an area of high curvature. Additionally, what we also showed as a part of our work is low curvature generally represents data that is well represented in the data set. So for example, there are more white cats in the data set, your loss landscape will be flat, versus when you have less data in your data set. Formally, we just define curvature as the sum of the eigenvalues, and we use the Hutchinson's trace estimator to calculate our input loss curvature. This is a quick recap of my previous research, part of my prelim. And in my prelim, I mostly focused on the security aspect, which is broken into 3, which is adversarial robustness, where I presented trend, which was a way to attack ensembles and also build better ensembles for adversarial robustness. I also presented results for methods for improving out of distribution detection using intra-class mix-up and norm scaling. And finally, we kind of proposed a new method to handle heterogeneous data so that models are more robust for changes in data distribution. Next, we'll talk about the first new work after my prelim, which is the privacy pillar. And the privacy pillar consists of two works. And first, I'll kind of go about the fundamental links that we established between privacy, memorization, and input curvature. This work was presented at ICML 24, and again, we'll kind of start with our visualization, but in this case, from a more practical setting. So here we have images from the ImageNet dataset, and this is equivalent to that white cat that we saw, which is this low curvature input images, and these are high curvature input images. Interestingly, this first row is the same class as this. So both of them, I think, are hummingbird, if I'm not mistaken. But if you can clearly see this is like very of the class, whereas these are hard. Generally, these are memorized, but these are more generalized. In this paper, we kind of talk about the links between these three components, which is privacy, input curvature, and memorization. So we firstly kind of talk about how curvature and memorization are linked. Curvature, generally what we show is upper bounds memorization. Next, we talk about how privacy links to input curvature, and also privacy links to memorization. Like the way I like to talk about it is like privacy is a fundamental truth. It kind of bounds both memorization and input curvature also is an upper bound on memorization. Just as a notation like slide, while this is like notation heavy, you really don't have to read this slide, but if you're interested, you can kind of go over it. But the idea here is input is X and Y, so there's images or labels. I like to use the examples for images, but this could work for any supervised statistical model, not just limited to deep learning models, but any supervised model. And we always think about data sets as S, which has M samples, and we also consider S remove I, which is all the samples with the I except the ith sample, and these are adjacent data sets. Algorithm A is nothing but SGD, right? So in most of our cases, we're thinking about SGD as algorithm A, and the network that is learned by the application of this algorithm is H, and loss function is L. In some cases, we might assume a bounded loss, which is capital L. This denotes green with respect to input. This is H is this the double derivative, and trace of H is input curvature. There are a few assumptions for this work, which I will kind of skip, but if you're interested, we can talk about the assumptions in a little bit more detail. This is like our fundamental theoretical contributions. While the equations look scary, I would say, even to me, the ideas are pretty simple. So in theorem 5.1, what we are saying is the memorization of a sample is bound by the average curvature over a bunch of models. So if I was interested in the memorization of a particular sample, I would calculate the curvature estimate, average it over a bunch of samples or a bunch of models, and that would be a good proxy for memorization. Our theorem 5.3 says the amount of curvature, the average curvature over the data set is upper bound by a privacy parameter and the number of samples in your data set. Finally, we kind of, you can put both of these together and kind of link memorization and privacy. So what this says is larger your, worse your privacy, more your memorization. So let's take the example of very strong privacy. Very strong privacy is epsilon is 0. 1 minus 1 will give you 0, which means at most you can have 0 memorization when you have best privacy, right? But generally 0 privacy is almost impossible to achieve, so there's always some memorization that always occurs. We kind of test all of these in practice. Our first theorem suggests a linear relation between memorization and curvature, and we kind of test that out on both CFAR100 and ImageNet datasets. These are averaged over 1,000 models because we have to take an average over many models. This is averaged over 100 models. We see pretty much linear trend. We can account for this non-linearity towards the end. The reason is we assume a uniform loss bound in our theory, that is all samples are uniformly bounded in loss. But if you account for the loss bound being a function of the number of samples, you can account for this non-linearity, and that is what is shown in the green line. We also test our link between privacy and input curvature. And here I have privacy budget, and here I have curvature values, and we saw it as e power minus epsilon is the upper bound. So if you were, the dotted line is the empirical fit, and marker positions are the. And finally, we also test our link between privacy and memorization. There's a big gap between theory prediction and empirical observation. Here, what we are saying is, in practice, we see lower memorization than what theory predicts for a particular amount of privacy. So for a privacy budget of 20, empirically, we're seeing average memorization around, let's say, 0.01, 0.001, but in practice, the theory bound says it must be much higher. The reason this happens is the way we train these private models is using something known as DPSGD, which is differentially private stochastic gradient descent, and that gives you a worst case privacy bound. So which means the privacy value here is actually worse than what is actually in practice. So that is why we are seeing this big gap. So if you were to use a better private training method, this gap would kind of reduce.
So what is the memorization of one and memorizing everything?
Memorization of one means if you were to include that sample in the data set, it would have perfect performance. It will predict it correctly. If you didn't have that sample in the data set, it would make a wrong prediction. It will say the complete opposite. So let's say I took a cat.
What you're plotting here is the average?
Yeah, average over the data set.
Average over the data set.
Yeah.
So what does one mean, that every sample is being memorized?
Yeah, at most every sample can be memorized.
Can be memorized.
Yeah.
So that is anyway a very, very loose bound, right? That is the maximum.
Yeah. So I think I think this graph is kind of, the scale is wrong. We should have just stopped about here. I think all of this stuff is not really making the case for us, but I think we realized that a little bit after. But yeah, it's a good question.
And how is privacy budget related to epsilon?
Okay, I just remembered. I'll kind of repeat the question for the recording. Yeah. I think the question was, how is privacy budget related to
The epsilon.
epsilon? Yeah. Privacy budget is the epsilon. Yeah. So it's, let's say privacy budget is 0, is like you have perfect privacy. I don't think we can hit 0 in practice because we won't learn anything. The way we tend to do this in practice is you add noise to the gradients, and if you add sufficient noise, you'll get privacy. Yeah. In summary, we kind of talked about the theoretical connections. Yeah.
So anything privacy budget of close to 0.
Yeah.
If it's higher than slightly greater than 0, everything becomes 1.
Yes. So maybe I can repeat the question. So the question was, if the privacy budget is anything 0, does it become 1? I think this privacy budget is e power. So I think this is in the wrong scale. It should have been in log scale, and then we would only focus on this piece where privacy is at most, let's say 5. Also, this kind of changes for the data set that you use. So if you were to use a different data set, you will get, at least the theoretical bound will remain the same, but this will kind of change based on the data set. So yeah, this graph is not in the right scale. Yeah.
So for the other bounds that you have shown the results for, go back.
Yeah.
To the slides. Just wanted to understand. So the markers are what you're getting from the empirical.
Then we have a model. So we have
Showed in the equation.
yes, and then we use that model to fit to that data. So the model would be going in the wrong way. So we have this. This is the model, right? So I put in a loss bound. M is the number of samples I have. Epsilon is the privacy budget, and C is something that we have to learn as or fit to. So this is the model, and we take that and we fit the red dotted points and the blue dotted points to that model, and that is the yeah. So C2 is a fitting parameter. Yeah.
And how did you derive those equations based on like foundational?
Yeah, so that's I would say the proof is an engineer's proof. And the way I do it is Taylor series approximation. A quick overview would be you want to break up your loss function as, let's say, the first order term, the second order term, and so on. And once you have the second order term, you can link that to curvature. And that is roughly the approach for the proof.
So, for example, this fits in very well, so that means the higher order terms definitely are.
Yeah, yeah. So one way we kind of skip the explicit notion of Taylor series is we assume Lipschitzness. When we assume Lipschitzness, it just lets us set the higher order terms to 0. So it's a way around.
Can you back to the very first one?
Yeah.
So here, the blue one. So what is the difference between the red and the green?
Yeah. So red is what is just this, assuming constant L. L is saying what is the worst case my loss will be. So this is an upper bound on the loss function. What happens in practice is for samples in the tail, so highly memorized examples, the loss can actually be significantly worse, or the bound will be larger because it's harder to learn. Whereas samples here, the bound will actually be lower because it's easy to learn. This red line is when you have a constant bound. This green line is when you account for the number of samples to change the bound. So the bound is roughly square root of m, where m is the number of samples in each of these categories. And if you account for that samples and use that as a loss bound, you will get this green line in both CFAR 100 and ImageNet.
So this is supposed to be an upper bound, green line.
Yeah, so there is some theory in terms of stability and generalization. There is this paper from 2002 which talks about what if you had n samples in your data set, what is a generalization guarantee for that sample. So this generalization error, so that is the error between your train, difference between your train loss and your test loss, the average, decreases as 1 by square root of m, where m is the number of samples in the data set. And so we use that to say, the loss bound is dependent on the number of samples in each subpopulation. And we use that to approximate the upper bound on L. And once we do that, we get the green line.
But the green line is supposed to be the upper bound on the curvature.
This green line is again a fit.
Sure, but based on your equation, it's supposed to be the upper bound less than equal to what is?
Yeah, so here we throw away the C.
On the other side. Okay.
Yeah, so it's, yeah. Yeah, I had a slide for questions. If you have more questions, I'm happy to answer. Yeah.
Maybe you explained it while answering these questions. But the L, is that the L, the chip's L?
No, we just assume the loss is bounded. So the maximum value, so for example, cross entropy goes from 0 to infinity. I am just saying choose a loss that goes from 0 to L. But this theory does work for cross entropy. We kind of go about that in the paper. It works for bounded loss or for cross entropy. When you have cross entropy, this L term goes away, roughly speaking. Like there's a little bit of nuance in the theory, but it'll also work for cross entropy. Yeah, next I'll kind of talk about the second privacy pillar, which is work that talks about membership inference attack. And I'll kind of give you a brief overview of what a membership inference attack is. I'll give an example in a ChatGPT case and an NLP case so that we can ground it easily. But in this example, we'll always talk about images. So let's say you have access to some model, but you can only send inputs to the model and observe its outputs. So it's a black box setting. And then you're given a particular training example. Now the question is, can you tell if this sample was used in training the model or not? So you have a black box model and a data point. You've got to tell if that data point was used in training the model. So the reason why we think about this as a privacy concern is, let's say that data was your data, and maybe somebody used this data. Maybe you wrote a paper, and maybe some LLM was trained on this paper without right copyright or whatever. Now, how do you tell if your article was used in training that model? That is roughly the question we're trying to answer in this case, but in an image setting. Right? So we consider image label pairs. So the way this started was we had already done this link between privacy, memorization, and input curvature. And we understood what input curvature means for a training example, and it's related to memorization. But what about, we can still calculate curvature on a test example. But what does that mean, and what properties does it capture? To do this, let's kind of quickly visualize this again. Here is a less snowcat and Garfield example that I like. These are low curvature images. They roughly lie in this flat landscape, and these are high curvature images that are more sharp in the input loss landscape. Now, if we see these test examples are higher curvature regions than the train examples. As we'll see later on, when you optimize a network, you not only optimize in the weight space, but you also optimize in the input space. So the gradient with respect to your input also goes towards 0 as you train a model. It's something that we'll talk about later. Using this, we can say, oh, if the test curvature, maybe we can think about a line that we can draw, like a threshold that we can set, and we can say, oh, this sample was used in training, this sample was used in training, this wasn't. And that's the way we'll think about membership inference attacks. The interesting problem here is, in our previous approach, we needed access to model parameters to calculate curvature. But in a black box setting, you can't access model parameters. So we propose a new method of estimating curvature without needing access to model parameters. So we just query the model a bunch of times, and we estimate curvature, and we call it zero order estimation. Effectively, it's a finite difference method. Zero order because we only look at loss rather than gradient or Hessian. We provide a little bit of theoretical reasons as to why we think curvature will outperform other methods in this membership inference test. The first thing we kind of look at is the scale divergence. This theorem just says, let's think about a distribution where the sample was used in training versus when it was not used in training. How do those two distributions differ? Right? So the KL divergence, larger KL divergence means the distributions are very different. Smaller divergence means they're very similar. So the larger this distance, the better you'll be able to distinguish between your train and test example. So what we can show is when you use curvature, you'll get this upper bound. And we can also do this for when we use loss functions or the loss function as a metric. Right? So we use a threshold based on loss rather than loss curvature. And once we have that, we can compare how well loss will perform versus loss curvature. And what we find is that curvature will do well when the number of data points in your data set size exceeds some threshold given by this upper bound. So we'll also test this and membership performance in the next few slides. This is just how we estimate zero order curvature. Here we just do 4 forward passes. F is your network, we do 4 forward passes, and we get our. A quickly skip this slide and go to the next one because it'll talk about the same thing. So here, our idea is we want to train a bunch of models called shadow models, and those will include certain samples in the training set versus others. So we'll have A with the query sample and A where the query sample that we are interested in is removed, and we train a bunch of models. And then we build a distribution for the curvature scores, and we estimate the mean and variance. And using that, we can do a likelihood ratio test. Once we do this, we can effectively do the complete membership inference attack. So given a sample, we pass it, train these models, we estimate our distribution parameters, then we test if it was likely coming from a distribution when it was used in training or when it was not used in training. These are some of the results. So since MIA is a binary classifier, we use AUROC and balanced accuracy, and these two are our methods. So one is the negative log likelihood ratio test and one is the likelihood ratio test, and we kind of get state-of-the-art results. So this was the previous state-of-the-art, this is our results. Additionally, when we're thinking about membership inference attacks, we also really care about having really low false positive rates. What do I mean by that? Let's say I tell you, hey, this sample was used in training. I rather not have it be a false positive. If I say it's true, it should really be true. So what we care about is really high true positive rates at really low false positive rates. So the big test is, where does this line cut the x-axis? So the higher this is, the better you are generally. So these are two aspects of performance for MIA. And our parameterized MIA does really well compared to previous methods. So this blue line is also ours. So there's a trade-off that you can make. If you give up performance at the bottom end, you can add performance here. But because this is in log scale, your AUROC will go up. AUROC is nothing but the area under this plot. We also test the other two things our theory says, which is how does data set size affect our performance compared to previous methods. And you can see below, let's say 20 or 30%, the red and the blue, which is our methods, are not doing as well as prior methods. But once you exceed that, our method does well. So this is what we predict in theory as well. Like once we exceed a certain data set size, we'll outperform other methods. In conclusion, we kind of built this train test distinguishability theory for curvature. We set up a black box implementation for curvature, and we validated that in experiments. Questions?
What does AU stand for in AU also?
Area under receiver operating. So ROC is receiver operating characteristics, and that is just nothing but, this plot is called ROC, and we just plot area under this curve. Yeah. Next, I'll talk about the memorization pillar. I think I'm a little short on time, but I will kind of quickly go through. The memorization pillar consists of two works. Both are like proxies for memorization. The thing that kind of sets the stage for this research is calculating a true memorization is very expensive. You have to remove a sample from the data set, train a model, add it, train a model, look at the difference in performance, and you have to do that for every sample in the data set. So generally, you have to train in the order of number of samples of models. So if you had 1 million data points, 1,000 to 10,000 models. So it's very expensive. Our goal was to kind of build faster proxies, and we'll talk about the applications of some of these. So the first proxy is called CSL, and it's about 10,000 times faster than traditional proxies. And we also established some theoretical connections in this work. To build intuition, I'll quickly talk about this loss trajectory and how this builds intuition. So here we have two images from ImageNet, and these are the loss traces for this sample. So for this hard example, the loss is high for a long time and it drops later in training. Whereas for these examples, it's learned early and stays low. And I have correspondingly put in like the true memorization score, which was calculated by Feldman and Zhang back in 2020 for ImageNet. And we can clearly see there is this correlation between when the sample was learned and the memorization score. And the loss is like pretty noisy, but if you average that, you can clearly see this average value is higher for the harder example. So this is like our intuition for our proxy. Instead of average, it makes a little bit easier in theory if you were to just look at the sum. But since epochs are constant, the average loss or the sum of the loss are roughly equivalent. And we use CSL or the cumulative sample loss as our proxy. So we define three things. One is cumulative sample loss, the other is sample learning condition and learning time. These are our contributions, I mean all of these are our contributions, but we are the first people to think about learning time and sample learning condition this way. So CSL is pretty straightforward. You take the loss of each sample and accumulate that over training. Sample learning condition is a little bit different. What we are saying is this is gradient of the loss with respect to input, and the average of that over training must go below a certain threshold, and we call that sample learned. Another option would be the loss goes below a certain threshold, you say it's learned. We are saying the gradient norm goes below a certain threshold and it's learned. This is mostly for convenience in theory rather than like more intuitive.
Why is it more convenient?
We use SGD in our proofs, and what SGD talks about is how this term, but with respect to W, changes over training. So they show that if you have the gradient norm with respect to W, it converges. What we show is this gradient norm with respect to W and input are related. So we can use this that convergence result to kind of talk about how this learning condition is met. And learning time is nothing but the first iterate or epoch at which this sample learning condition is met. We make a few theoretical contributions here. I think this is a very interesting result, which is input gradient is a lower bound on the weight gradient norm. And once we have this, then we can talk about that input gradient converges as you train. So this is what I was talking about earlier when I said, if you train a model, not only do you converge in your parameter space, but you also converge in your input space. And that lets us do that membership inference attack and build intuition about that. We can also talk about how learning time is linked to memorization and all of the three links, right? Cumulative loss and learning time. And I will kind of quickly skip the details here, but all we can say in this theory is for a group of samples, unlike the previous one, we cannot specifically talk about memorization of an individual sample, but we can talk about groups of samples. And this is exactly what we test. We take a group of samples, take the average, and we plot a memorization score versus learning time, which is predicted by our theory to be more or less linear, right? And similarly, learning time and CSL are more or less linear. We also kind of test the CSL memorization, which is the important link, and it's also more or less linear. And this non-linearity, again, similarly to previous one, can be accounted for non-uniform bound. We also tested how good of a proxy CSL is compared to true memorization scores, and we compare it against a bunch of other proxies for memorization. And clearly, our memorization proxy is pretty good. This is cosine similarity, this is Pearson correlation. We get a pretty strong correlations. So the question is, okay, Deepak, you presented a bunch of theory. What's a use case, right? Tell me about a use case. A good use case is identifying mislabeled examples and identifying duplicates in the data set. To do so, what we did was we intentionally introduced label noise into our data set, 1%, 2%, 5%, 10%, and so on. And we use CSL as a threshold to identify if it was mislabeled. So if the CSL of the sample exceeds a threshold, we say it's mislabeled. And if you do that, you get state-of-the-art mislabeled sample detection. Similarly, we also can do this for duplicates. So same image, but duplicate labels, and you get state-of-the-art performance. In summary, we kind of show a new proxy for memorization, link it to learning time and memorization, and we show some practical applications. Questions? Yeah. I'll kind of quickly go over the final work, which is again faster than CSL, I would say. The question is, how do we go faster than free? Because CSL, all you need to do is train and you get your loss. And the faster than free is to not train completely. And that is what we kind of do here. Instead of loss, we look at the input gradient norm. And here what I have is epochs versus sample gradient. And if roughly, and it drops off. And this peak roughly corresponds to the lowest validation loss in your first descent phase. Generally, deep neural nets do double descents, so the loss decreases first, increases and decreases. So this is validation loss, not training loss. And this corresponds to this lowest validation loss. In general, this happens when your model goes from memorization domain to generalization regime. So this is when roughly peak memorization is happening. So you can stop roughly here and you can get your full, you can compute your proxy here and you can be done. So you can save a lot of effort by only stopping early. And the interesting thing is this increase and decrease is only a property of CSG, which is the sample gradient, and not CSL. So we need CSG to get that performance benefit.
So for my understanding,
Yeah.
sample gradient is, so you take a sample
Yeah.
input, right, training sample,
Yes.
right?
Yeah.
You compute the gradient of loss associated with respect to that input.
Yes. So if you were to do adversarial attack, you would get that gradient and you would perturb it that way. We just take the norm of that and plot it.
So can you give me an intuitively why that P corresponds to that?
Yeah. Okay. So I'll go over it, and like this peak was a lot. We didn't really understand why this peak was happening, but the reason this happens, I can give you a quick. Actually, in a couple of slides, I will talk about it. So I will just wait until then. Yeah. So we use this to do early stopping. We show some performance on that, and we can do bias discovery. I'll talk about bias discovery, but quickly, the easy examples are all red here, and this is an unintentional bias on CFAR and CFAR 100 images. And we can again do this mislabel detection and duplicate detection similar to CSL, because all the properties similar to CSL. Again, this is this training trajectory loss, building the same intuition. CSG, or like sample gradient, also has a similar property. Easy samples are learned earlier, the average is low. Hard examples are learned later, average is high. Yeah, so this is the plot that will answer Professor Gupta's question, which is, why is this peak happening? So the input gradient norm is linked to weight gradient norm. When we train a model, the weight gradient norm is guaranteed to converge, right? So we know it will converge. But the input gradient norm is bounded by this weight gradient norm and the weight norm. So you take a product of the weight norm and the input weight gradient norm, that is the upper bound on input gradient norm. So as you train, what happens is initially SGD pulls it to learn your loss function, right? So it's improving performance. But the issue is the weight norm goes up, and then you have weight decay factors in SGD. Once that kicks in, or if you don't have weight decay, SGD has an implicit bias towards low weight norm solutions. That will kick in and it will pull the weight norm low. So since this is the upper bound on your input gradient norm has the same, roughly the same peaky behavior. So you can either use this weight norm or your input gradient norm to figure out when to early stop. And another reason, or another evidence to kind of talk about why memorization is, we're switching regimes of memorization to generalization is, here I have like this blue plot is epoch-wise similarity to memorization, and that is Feldman-Zhang's true memorization. And it goes up as we train. At peak memorization, you get peak correlation, and then it drops off as you train and drops off. But if you look at CSG, it goes up, it stays there, and it flatlines. So this is what gives us our benefit. You can just stop right here and get a very strong memorization proxy. Again, for this work, we kind of established theoretical links between CSG, learning time, memorization, and CSG. I'll kind of skip this for time. But we expect linear relations. That is what our theory says. And we validate that in practice. So this is for CFAR100 and ImageNet. We kind of see the linear link between learning time and CSG, memorization and CSG.
The right one, you call it.
Oh, this one? Yeah, again, this I will point to the nonlinear uniform bound. All of this is assuming uniform loss bound, and I think that is one of the limitations of this approach. So while it works for cross entropy, the cross entropy bound is looser, so this is all not very linear. I agree. And we can also do the same thing that we did for CSL, which is talk about how good of a proxy CSG is using Pearson correlation, which is core, and CS, which is cosine similarity, and a bunch of baseline methods. And I've also put in like compute costs, so we can clearly see a lot of benefit. And the previous state of the art was, I think, curvature and like loss sensitivity. We clearly beat them, but with significantly lower compute cost. This is a little bit of evidence showing that we capture, if you were to early stop using weight norm or input gradient norm, you'll have all of the benefits that you would get if you did validation based early stopping. Here we're only considering early stopping at the first lowest validation point rather than the second descent. The later you go in training, the worse off your privacy is. So for a privacy perspective, we are interested in the first descent. And so I'm talking about, I present results for membership inference attacks, which tests how good of a privacy benefit you get by early stopping. So last epoch is, so the larger those numbers, the worse your privacy is. And the last epoch performance is pretty high, which means you have bad privacy. If you had stopped at earlier point, which is the first lowest validation loss, you would get lower performance, which is better privacy, and you'll get similar benefits when you use input gradient norm or weight gradient norm based early stopping. Again, we can do mislabel detection, and the interesting thing about mislabel sample detection with CSG is it works really well at higher noise levels compared to lower noise levels. And we see, like for example, CFAR100 is more noisy, so it outperforms other methods all the way from the beginning from very low noise levels. But for CFAR10, which is a little bit more clean, we need a little bit more noise in to kind of get improved performance. But one thing to observe is these are really close, right? So it's not like this is way off, this is 0.01 off. This is in 0 to 1 value, so this would be like 98.09%, and this is 98.19%. But still, this is within the margin of error, so this is a statistically significant difference. And we can also do duplicate sample detection. Again, we get really close performance on CFAR10. CFAR10 is more clean, and CFAR100 is a little bit more noisy, so we kind of outperform curvature here. And finally, this is an interesting result that only CSG can do, and CSL doesn't pick up on this, which is bias discovery. For example, curvature picks up similar biases, CSL doesn't, CSG does, so it's like a trade-off. As you get higher order information, you pick up on biases. Here again, like I discussed before, the red examples show up as easy, which is an unintended bias in the data set. And here, low contrast dark images from fashion MNIST show up as hard examples, which is also an unintended bias. In summary, we kind of talked about very fast proxy, so theory to link these proxies, and some practical applications. In conclusion, I presented 3 pillars of my work, which map to the trustworthy AI pillars: memorization, privacy, and robustness. And 2 works here, and works from my prelims here. And before I conclude, I'd like to acknowledge Kaushik for all of the, I think without Kaushik, this would not have happened. I have lots of stories, but now is probably not the time to go over them. And my committee members for all of their help and guidance, Professor Jung, Professor Gupta, Professor Anand. My parents, friends, members of NRL and alumni, and also all of these funding agencies. This is just more of disclosure when this goes public. And yeah, that's it. Thank you for listening to some of the boring pieces of theory, I would say, but interesting applications. Happy to take more questions.
Any questions for that?
Have you explored membership impacts in technical models?
Good question. So I'll just repeat it. So have I looked at membership inference in generative models? No. This is technically the theory should hold for any supervised model. So since all language models are technically supervised models, they are equivalent to recognition models or classification models, it should hold true there. But the question is, like, does it translate to there? We need some empirical evidence to kind of say, does this transfer? Yeah, I haven't looked at it.
Any other questions?